Hi, today we're going to get into something really fun. We're going to talk about quadratic functions. So many of you have done this before, but let's do a little review anyway. So a quadratic function is any function that can be written this way. F of x equals a times x squared plus b times x plus c. Now this is where a, b, and c are just plain old numbers, okay, and x is the variable, okay. And for this to really be a quadratic and not a line, a has to be a number. It can't be zero, rather. It has to be a non-zero number. Okay. We can come up with some examples of quadratic functions. For instance, your favorite x squared. Okay. 3x squared minus 1 x plus 9 times x minus 2. The only weird thing is this one doesn't have a square in it, but you'll notice that if I were to multiply this together, I would end up with a square term. So the big thing about a quadratic is that it's got a square. It can't have a cube. It can't have x to the cube, can't have x to the 3, to the 4, to the 5. It has to be at the most x squared. There must be a square term. There can only be a squared, not a third, not a fourth. So, a graph of a quadratic function, and I don't know why these are like this, has a special name, and it's called a parabola. Okay? So in the same way that we think of a linear function as having a graph called a line, so the function is called linear, but the shape is a line. Okay? Same thing with quadratic function. The function is a quadratic. The parabola is a graph of a quadratic. Okay? A couple things to notice. So they have this kind of nice smooth curve. You've seen this before a bunch, I'm sure. A couple things to remember is that these lines will continue to move out, okay, as they go up in this direction. They will also continue to move outward. Okay, they never get vertical. Same thing here. We'll continue to go that way and that way at the same time. Not at the same rate. Okay, they're gonna go off in slightly different rates, but they will continue to climb and they'll continue to get wider. Okay. The other thing to notice is something called an axis of symmetry. For this line here, pardon me, for this parabola, this is the axis of symmetry. Notice how it's the same to the left of this line and the right of this line. So axis of symmetry is the x value where the graph looks the same on both sides. That's your axis of symmetry, and it's a vertical line. Okay? Your vertex is here, or on this graph, it's here. It's going to be the highest or lowest point. Okay? So vertex is your highest or lowest point, and your axis of symmetry is the x value where it looks the same. Notice something nice about this. The axis of symmetry is the same as the x value of the vertex. Okay? They occur in the same spot. The axis of symmetry goes right through the vertex. Alright, let's look at some functions here and decide whether they're quadratic or not. Okay? Let's look at the first one. Okay? The first one is 2x minus 1. Now we should all recognize that as a line. Okay? It's the graph of a line. This is not quadratic because there is no x squared term. Let's look at the second one. So this is a no. Okay. The second one, okay, y equals x squared. Well, in this case, if I look back at my definition, ax squared plus bx plus c, a is 1, b and c are both 0. That's okay. B and c can be 0, just that a cannot be 0. Good. That's quadratic. This next one, okay, again, we have 2x squared minus 1. It has a squared term. That's okay. There's nothing else. I don't have a cube term. I don't even have an x term. But a quadratic needs to at least have an x squared term. Okay? If it doesn't have an x term, we're okay. If it doesn't have a constant term, we're okay. This one is also quadratic. Let's look at the next one. Okay? This is 1 over x. Okay, this should look a little strange, right? It's completely in a different form. I have a numerator and a denominator. Okay? This is a rational function, 1 over x. I don't have anything that looks anything close to a squared term. So this is not a quadratic. Let's take a look at this one. This is tricky. I don't see a squared term, but I see two linear terms. I have a line 2x minus 1 and a line x minus 1, or 2x plus 1 and x minus 1. But let's see what happens if I FOIL this. Okay, remember, firsts, outsides, insides, last. If I FOIL it, I'm going to get 2x squared. Aha, that's my x squared term. Let's see if I have anything else that I need to worry about. I have a plus x. Okay, I've got a minus 2x. And I've got a minus 1. Oh, well that's okay. This is 2x squared minus x, because x minus 2x is just minus x, minus 1. So 2x squared minus x minus 1. That's okay. A is 2, b is negative 1, c is negative 1. This, too, is a quadratic, even though it's in a slightly different form. This one? Yeah, this is fine. 7 is A, negative 2 is B, 9 is C. This is fine. Okay, this one down here, I have 3 times x. Well, I can't simplify it at all. It's pretty simple. But there is no x squared term. That's a tip-off right there that it is not a quadratic. Unlike this situation above where there wasn't an x squared term when I had it here, there was a way to simplify this so that I had an x squared term. There's no way to rearrange this so that I get an x squared term. And finally, this last one. I know fractions are bummers sometimes, right? Well, let's take a look at this. This is a number. This is a number. I have a number times x squared plus a number. If we think back to our definition, ax squared plus bx plus c. In this case, a is 3 halves. That's okay. B is 0, there is no term with just an x, and C is 5/4. Well, that's fine. It doesn't matter if the numbers out in front are fractions or whole numbers. Okay? It's going to work either way. Alright, so now let's just practice graphing a little bit. So we're going to play with this function for a minute. Y equals negative x squared plus, minus x plus 4. So here's what you want to do to graph when you're first starting out with quadratics. The first step is to create a t-table with x values ranging from negative 5 to 5. Now I'm choosing negative 5 to 5 because that's usually a good range. Sometimes that'll be a poor range. Sometimes you're just going to have to feel it out a little bit. The next thing is to calculate values in your t-table. Okay. Then we're going to draw and label your axes so you can include each data point. Then plot the points. Then connect the points with a smooth curve. Okay. And we're going to go ahead and try to label the vertex and the axis of symmetry best we can. Let's go for it. Okay. Here's my t-table. I've got my x values going from negative 5 to 5. My y values I'm going to throw in here when I get it. So what I'm going to do to get my first y value is I'm going to plug negative 5 in for x, because this is the x column, into this function up top here. Erase that. Okay? So I'm going to put negative of negative 5 squared minus negative 5 plus 4. I'm going to put that in. If I do that, I'm going to get a part of positive 16. If I put a negative 4 in, you get negative 8. A negative 3, negative 2, and all the way down to 5. Now, I haven't done this out slowhand. I would very much like for you to make sure that you are able to plug a negative 5 in here and verify that you do get a negative 16. Okay, so make sure you're doing that on your own. Plug in a negative 5 into that equation, verifying that you get a, this should be a negative 16. A negative 16. Okay, we need to get a negative 16 there. Alright, so we get a negative 16, negative 8, negative 2, and so on. The next step is to set up our axes so we include all the values. So my x's should go from negative 5 to 5 at least, and my y's should go at least from negative 32 up to 4. Now I usually try to go a little bit lower and a little bit higher, so negative 33 to 5, something like that. Okay. And again, this should be negative. So here is my axis. It goes from negative 32 to 5 and negative 5 to 5. Okay? And what I've done here is these red marks, I've plotted each point from the table. So this mark right here is the point negative 5, comma, negative 16. That's from this information right here. This second point here that I'm circling is negative 4, comma, negative 8. Negative 3, comma, negative 2, and so on and so forth. And so we start to see a pattern. Oh, that's pretty nice, right? Okay, now we've got a pattern of dots, and we can start to see the shape coming into existence. The next thing I'm going to do is try to connect these with a smooth curve. Okay, and you can see in my next slide here, I've tried to do that freehand best I can. It's not always going to come out perfectly. So one thing that we should look at here is notice how we go through the point -1, comma 4. That's the height of 4 there. And 0, comma 4. These are the same height. Because we know the shape of a parabola is totally curved, it's not going to be flat between these 2 points, right? We know it's got to go up between those 2 points. So the vertex is going to be right in here somewhere. I'll make it green, make it a little bit bigger here. Right in here. Boom. There's the vertex. Okay. That also means that we can easily find the axis of symmetry. The axis of symmetry will go right here. Boom. There it is. So that if I were to try to fold this in half like a piece of paper, it would look exactly the same on one side as the other. Now, you're looking at this, and I know it kind of looks unbalanced, okay? Because it looks like one side is longer than the other. But just remember, you have to keep in mind that it's not that this side is shorter than this side. Both sides continue off the paper in either direction, okay? So just because I've stopped the graph here doesn't mean that the thing is lopsided. If we were to continue it in both directions, it would look perfectly symmetrical about that green line. Okay, so I want us to take a look at a couple other graphs here and see how they compare. Now we've done this with absolute value functions already, so this shouldn't be too complicated. Let's start with your basic x squared function. This is your most common parabola, okay? We're going to get the point 0, 0, the point 1, 1, the point 2, 4, and so on, okay? The point -1, 1, -2, 4, -3, 9, and so on. So we get this nice parabola here. Let's see what happens as we start to alter things. We go to the right. I want to go to the right on this one. What happens if instead of squaring x, I square x minus 1? Okay. Now this is happening to x. Okay. So whatever transformation is happening here to the graph, it's happening to x, not to y. Okay. So it's going to happen left to right. And in this case, when I subtract from x, it moves the graph to the right. Okay. We talked about this in class in particular with absolute value functions. Okay, so these graphs are the same thing except this one here, the second one, I've moved to the right 1 unit. Okay, now let's go back down to this graph over here, this function. So I've taken this same picture now, and now I'm going to multiply this function by -1/2. Now this does two things. Okay, it's going to compress, and it's also going to reflect. So this negative, okay, this negative is what sends everything downstairs. Pardon me. Okay, it reflects it down. So 1, 1 is now down below. 0, 1 is down below. Boom. 2, 1 is down below. Okay, 3, 4 is down below. But something else has happened at the same time. That negative what sent things down. But look at where they went. Instead of the point 1, 0, 1 going to the point -0, -1, it's gone from the point 1, 1 to the point 0, 1 originally. That's where it was on this graph. And it sent it not all the way down here where we thought it was going to, but it sent it halfway down. Likewise, if I look at this point on the original graph, okay, this point here, the negative should send it straight down from 2, 1 to 2, -1. It doesn't though. It sends it down halfway. And that's what the half is doing. The half says send it, but send it halfway. Okay. The negative says send it down halfway. So this -1/2 is doing two things at once. It's sending everything down. It's reflecting over the x-axis. But it's also compressing it. So everything gets smushed closer to the x-axis. Okay, in the y direction it gets smushed. Okay, and then finally this last transformation takes what we had here and you can see it moves everything up 2 units. kind of interesting, right? So let's see what happened from picture number 1 to picture number 4. Well, picture number 1 is a parabola with a vertex at 0. Picture number 4 is a parabola with a vertex at the point 1, comma, 2. Okay? And it's also slightly different in shape. Instead of it being the regular size, we think of this as more the regular size, it's been compressed by a half. And it's been flipped over. So this negative is flipping things over, the 1/2 is compressing, and the vertex moved from 0, 0 to 1, 2. A lot has happened.